but also for people who have just acquired the equipment. You know, this is the first time this laboratory has been offered, you know, and you know, I hope I do a good enough job, Dr. Tyrell. So we'll see. You know, when Equinosis first started selling this equipment to veterinarians, it actually came with a full day of demonstration and training. And you know, that's sort of what this laboratory is going to be like. But if you're interested in finding, oh, I'm on the wrong slide. Sorry. Yeah. But if you're interested in finding out more information, you can go, and if you have the 6th edition of Adams, there's a chapter in there on how to work through the software and how to do the analysis, what the plots mean. And also you can go to the Equinosis website. I thought I had it listed here, but I don't. You can go to the Equinosis website, and on that website are training videos, very short little videos, because I know a lot of people don't have time to watch a long video, but there's very short training videos on how to work through the equipment and how to interpret the analysis. So helping with this laboratory is going to be Dr. Eric Adams. Where's he at? There he is, right here. From the Equine Medical Center of Ocala, Dr. Mike Major. I saw him come in the back. You probably know him from Oak Ridge. And both Dr. Adams and Major have been using this equipment for, I think, over a year, maybe for over 2 years, right? Something like that, yeah. And also Dr. McCracken, Megan McCracken, there she is. She was a resident, spent 3 years at the University of Missouri, and is now in private practice. It's called Rhinebeck Equine. Oh, I'm sorry, something like that. I'm sorry. Rainland Farm, okay. So I really need to point out that we could not have done this laboratory without the Bear County Mounted Patrol, Mr. Officers Bill Scheel, and right there, and Bill White. They're supplying the horses. They've really helped with the donuts and the coffee, and they're going to help, you know, film, and they really have been. I looked at all of the horses yesterday, and they drove me all around and helped me with that. So, you know, that's. What's it? And yeah, we did a Zumba class before. But yeah, so thank you very much. There's no way we could have done this without you. So and the agenda for this first laboratory is going to be, first I'm going to just give some introductory comments on the software and how to instrument the horse and how to work through the software basically. And then Dr. Adams is going to give a short presentation. And Dr. Major may say a few words also on how he uses the equipment. And then we're going to break and go across the street. We have 4 horses. Actually, we have 6. And but I think probably we'll use 4. And so we're going to break into 4 groups. I actually had groups made up, but it doesn't matter. Just break into 4 groups, and then put the equipment on the horse and trot it back and forth, look at the results, and then go to the next horse. I mean, it's instructive, I think, to at least have the experience of putting it on multiple horses. So I would just go to the next horse. I think we decided that we're going to leave the sensors on the horse. And okay, you can. Yeah, so we'll just, instead of taking, so each group is going to have a system. Okay, and then I was going to have you take the sensors off and everything. You can just take the system and everything go to the next horse. But I think it's probably best just to take the group and go to the next horse and leave the sensors on. But you know, we'll figure that out as we go. Okay, so first let me try to point out, make it clear what this equipment is. You know, this is only an aid for veterinarians. In my personal opinion, it's completely useless in the hands of somebody who doesn't know what they're doing, meaning know what they're doing in the sense of doing a lameness evaluation on the horse. In my opinion, the more experienced you are at doing lameness evaluation, the better that you're going to get the most out of the equipment. This equipment basically increases your sensitivity at detecting and evaluating lameness. That's all it does. But in my opinion, that's a lot. It does it much the same way that a microscope increases your sensitivity at picking up. It increases your spatial resolution, and this equipment increases your sensitivity because it samples faster than you can sample. The sensors pick up motion at 200 times per second, and a human just can't do that. Okay, so it's not really computer aided. It's more of sensor aided evaluation of lameness. Just increases the sensitivity of your temporal resolution. So that's why it's useful. That's one of the reasons why it's useful. The second reason why it's useful is because it eliminates bias. And that's because it's an objective method of lameness evaluation. As humans, there's no way, we are all subject to bias. And that picture down there at the bottom left, actually those horses are the same color, okay? And the only reason, and there's no way that we can tell that because of the context, the visual context, the field that they're in. But objectively, if you took a little eyedropper and sampled the color there, you would very easily see that they're the same color. And you could say the same thing about bias in the time domain also. This is in the color and spatial domain. There's humans, any kind of subjective evaluation is going to be subject to bias. And this equipment eliminates that. It is objective. And even though that's a very simple concept, it's kind of hard to appreciate. So this equipment is definitely not a replacement for veterinarians. You still have to do the work. Okay, you still have to do the lameness evaluation. But I think once you get good at working through the software, and it's not really that difficult, you can definitely use this equipment to speed up your lameness evaluation, primarily because of the increased sensitivity. So for instance, a lameness that might have been a little bit confusing in the past, it becomes less confusing, so there's less time trying to decide what to do. Also, sometimes I do many less activities now with the horse during my lameness evaluation, like flexion tests and lunging. If I can measure, I say see, but if I can measure the lameness, even if I can't see it, with the horse trotting up and down in a straight line, that's what I do. I don't go do all the other stuff. So because of the increased sensitivity, again, once you get used to working through the software, it will definitely speed up your lameness evaluation. It's not an encumberment on your normal lameness evaluation once you learn how to use it. This equipment is only sold to veterinarians, and it's only sold to licensed and practicing veterinarians. If you can't get licensed, you can't get the equipment. The equipment is in need of a skilled veterinary examiner to interpret the results. Not that you're going to have to do a lot of statistical analysis in your head or anything like that, but and the reason the more experienced veterinarian will get the most out of it is because the experienced veterinarian, because this equipment is more sensitive, it makes the gray areas bigger. So only the experienced veterinarians can interpret those gray areas. Okay. One of the first points I wanted to go over, which will clear up, only sold to licensed veterinarians. I already went over that. Sorry. Okay. One of the first points that I think is very important to emphasize, and actually it can clear up many questions about, or confusions about, especially for instance, why does the equipment disagree with me sometimes? Okay. And and the point is, why do we put the sensors where we put the sensors? And this is related to that concept. We put an accelerometer on the head, and we put an accelerometer on the pelvis, and then the sensor that we put on the right front leg is a gyroscope. It just measures where the right front leg is. The reason that we did that was because, we did the homework many years ago when we decided we were going to develop an objective method of lameness evaluation. We didn't know what we were going to measure. Okay, should we measure the length of the stride? Should we measure, how the leg moved through the air, abduction, adduction? Should we measure, how the horse's body sways or joint angle changes? Okay, and so we didn't know what to measure, so we collaborated with engineers. And we said, we don't know what to measure. We said, well, go back and measure everything. So we did. We measured everything. We put markers all over the horse's body, and we measured horses for years, hundreds of horses, sound horses, lame horses, horses that we knew where they were lame because we induced the lameness, and we collected everything. And we gave this to the engineers and said, please find for us the best place, the best motion parameters to use to detect lameness. And they came back and said, okay, look at the torso. Look at the vertical movement of the torso. So that's why we put the sensors on the head and on the midline of the pelvis, because that's the best place to look at vertical motion of the torso. So for instance, we don't measure pelvic rotation. I know some people look at that. We don't measure leg movement at all. Okay, so sometimes you may see something that you have associated with lameness in the past, some kind of pelvic rotation movement or leg movement, but the horse is coming down on that leg and pushing off that leg equally as the other side. And so it's not going, if the horse is coming down on a leg and pushing off on a leg equally, one side to the other, it's going to measure that the horse is sound, because that's what we found by investigating what was the best indicator of lameness. That's not saying that some horses that move their leg like this or rotate their pelvis like this or have a hip hike or hip dip, that doesn't mean that in certain cases would not be a good indicator of lameness. Okay, but that's not the most sensitive indicator of lameness. So that's why we put the sensors where we put the sensors. Okay, and this approach to measuring lameness, basically looking at the vertical motion of the torso is very logical. It's very straightforward. If a horse is painful on a limb when it's landing on the limb, that's going to affect the vertical deceleration of the torso going down. If the horse is painful when it's pushing off of a limb, that's going to affect the acceleration on that half of the body. The acceleration of the torso that results from the horse pushing off that limb. That's how we separate between impact and push-off. Okay? We look at whether it's affecting the deceleration or the acceleration. Okay, so that's really, that's all I'm going to say about the theory or the technique that we use to analyze lameness in the horse is really a fault detection technique. Okay, it's a common engineering analysis that they use for it's a vibration analysis that measures like the flatness of surfaces or lack of defects in the horse. When it's moving, when it's trotting, the torso is a vibration. It moves up and down just like a vibration. So that's the technique that we use. If you want to know more about it or really dive down into it to understand the mathematics behind it, you can. All that stuff is online and available, but we're not going to go through most of that here. But it's a fault detection technique. So one sensor is placed on the head. One sensor is placed on the sensor on the head is placed. The horse wears a head bonnet that we have made for the horse. Some horses, all of these horses today, by the way, you can put the head bonnet on with no problem. Occasionally you'll come across a horse that's head shy and you can't, and you can actually put the sensor on the crown piece of the head halter if you want. But the head bonnet is better because the sensor is sitting in the most optimum place, okay, which is like right behind the ears. And so the head sensor goes on the head with the head bonnet, and the pelvic sensor, which is also an accelerometer, goes on the midline of the pelvis between the tuberous sacral. And it's usually the most dorsal aspect of the pelvis. You can, there's a little piece of 3M dual lock tape that you press down into the horse, and it sticks to the skin pretty well, and then you snap it into place. It's like industrial strength Velcro, so you gotta push it in and snap it into place. We have this pelvic clip you can use for horses with long hair. For horses with short hair, it works best if you just press it down into the horse, and then I use duct tape to push it down further into the horse. And it's important to get this on midline. You know, we've done this fault detection technique is dependent more upon getting the sensor on midline than it is about how the sensor is oriented, okay? Because the fault detection technique that we use is it's a shape analysis technique. So if you have that sensor and it's tilted like this, that's just going to decrease because it's a vertical accelerometer, that's just going to decrease the size of the signal. The shape is going to be the same. Okay, so it's more important, but if you get it off center, then it will measure maybe asymmetry. So it's more important to get the sensors on the center of the horse's midline. Okay, we've done experiments where we have determined that you have to get that, and it's more important than the pelvic sensor, you have to get that pelvic sensor off midline by somewhere between 1/4 and 1/2 the width of the sensor before you start manufacturing results. Okay, so try to get it on midline. I like to tape my pelvic sensor down like this. I use good old duct tape. Any kind of tape will do. And you want to push it down into the horse, okay? Because you want that sensor to move up and down with the horse. If it's stuck to the hair only, then it'll wiggle. It'll move independent of the vertical motion of the pelvis. So you want to get that sensor stuck down onto the horse. Okay, so I use duct tape for that, and the clips work just as well. Okay, so for horses with relatively short hair, that's what I use. Okay, putting it on midline, I went over that. Okay, the pastern sensor is put in this pastern pouch that was designed for the horse. It's very important. Come on in, doctor. I'm sorry. Okay. You want me to start all over? No, I'm just kidding. Sorry, we won't start over. Yeah, let us start from the top. Oh, thank you, sir. Thank you. Yeah, I will start. So, okay, this pastern sensor goes in a pastern pouch. It's very important that this technique that we use, that the pastern sensor gives no information at all about the amplitude of lameness. All it does is just an event marker. It just tells us when the right leg is on the ground. That's it. And we use it to insert into the pelvic and head signals to determine, okay, start here and do the calculation. Okay, so it's very important that we get that start correct. So, like for instance, you put this on the left leg, okay, you get the opposite results because it thinks it's on the right leg. Okay, so you have to put it on the right leg. Okay, I'll get to a story about a veterinarian the owner said, well, I think that is causing the horse had a right forelimb lameness. Because I think that's causing the horse to have a lameness in the right front. And he goes, no, I'll show you. And he put it on the left front. And then it showed the horse had a left forelimb lameness. And the owner said, see, Okay, but in reality, it proved that the horse had a right lameness, because if you put on the left forelimb, you get exactly the opposite result. Okay, because the event marker is 180 degrees opposite of what it should be. Okay, it has to go on the right front leg. It also has to stay on the dorsal surface of the right front leg. Okay, if it rotates around to the back, then it's like putting it on the left front leg, because it's a gyroscope. It measures angular velocity. Okay, so it's gonna and it measures the direction of the angular velocity. So if you put it on like this, then everything is going to be the opposite. Okay, so if you're going to exercise the horse vigorously, like the lunge, I like to put some elasticon around it, because the weight, the inertia of the inertial sensor will bring it around to the back if the horse is really exercising. So you have to be careful about that, and that's why I use some elasticon, just one little strip around the top to keep it from rotating. Okay, there was something else I wanted to say about that pastor. I can't think of what it was. Oh, that's the other thing. Well, I think I covered this in the advanced laboratory. But all of the lameness calculation comes from the sensors on the torso of the horse. This is just an event marker. Okay, so does this change the way the horse moves its leg? Well, maybe it does, but it doesn't change the vertical motion of the torso. We've tested this over and over again, many times, many different ways, by putting sensors on other legs and then putting equal sensors on both legs, and putting this 28-gram sensor on the right front leg does not cause the horse to have a forelimb lameness, or it does not cause the horse to be asymmetrically moving to think that the horse has lameness. Okay, so now you have your horse instrumented. I'm going to just briefly now go through how to work through the software and the basics. Okay, that the instructors are going to help you through that. But the basics are in these steps. First, you get the computer in your hand, and you put information into the computer about the horse and owner that you're collecting. Okay, that's the first thing you do. You see how to do that. Okay, and then also you pick what sensors you're going to use, because most systems come with multiple sets of sensors. So you put your horse in owner information, say, okay, I'm going to use this set of sensors. Okay, then you connect to the sensors, and then you're going to after you connect to the sensors, you then have to enter into the computer what it is that you're doing. Are you evaluating the horse trotting in a straight line? Are you lunging the horse? Are you doing a flexion test? Are you doing a block? Okay, so then you enter trial information. We call that trial information. Okay, then you collect the data. You see it being collected. Then you stop, and then you analyze it. Okay, and there's a button that you just press, and it runs through the analysis. So that's in general what you do. Enter information first about the horse, owner, sensor, collect, or connect to the sensors, information about the trial, collect, analyze. That's in general how things go. So, but specifically, you'll see an icon on the desktop. It has this. It has LL. You just click on it. Double click. It takes a little bit of time to understand these tablet PCs and using the stylus, but it's a fast double click. And that opens the icon. Okay, then you enter the owner information. Did you have that pointer? Okay, good. And then just again
Top button.
Okay. Up here you'll see 3 drop downs. This is the sensor drop down, horse drop down, and this is the owner, manage horses and owners. Drop down. So this is where you're usually going to be working. So you open this up, and the instructors will help you enter maybe just say group 1 or something for your owner. Okay? And then the horse name and things. So this is where you work. Okay. And there's this little go button right here. that activates anything that you select. So first thing to do is just pick Manage Owners and Horses, hit the Go button. That will open up windows for you to put the information in about the horse. It's pretty self-explanatory. Okay, so once you've got all of that information in there, and oh boy, can you just tilt that up a little bit? Once you get everything entered into there in the sensor group, then there's a button right here that says Connect the Sensors. You click it, okay, and it will takes a few seconds, but you'll start to see you see some information up here. But then once the battery voltage on the sensors, this is probably the only slide that's too low.
Okay.
But once the battery voltage on the sensors is shown to you, and it's color coded, green is fully charged, yellow is starting to get a little bit low, red is, you better charge them up. Okay. Usually you got maybe about 15-20 minutes if it's in the red. The sensors will last all afternoon. You won't have. I don't think you'll get into the red. Okay, so once you see the battery voltage shown here, then it's ready, and then you hit Start. And here's entering the information about the trial. So for this laboratory, we're really gonna, unless we get really good at it, but we're gonna start out by trotting the horse in a straight line, back and forth in a straight line. But that's where you would enter it, and then once you put that in there, then you just hit OK down
Is there
here.
a drop box for that, Kevin? You just type that in?
Yes. There's a drop box.
Okay.
You hit this and
Click on straight.
Yeah, the straight is the first one.
Yeah.
So almost everything we tried to make it so that you shouldn't have to type anything in, because typing with that stylus is a pain in the rear end. Okay. So almost everything is in a drop down. Most, like for instance, when you're blocking, the limb that you're blocking is here, and then the blocks. Well, if you pick a limb to block, all of the blocks for that limb will show up in the drop down. Okay, but you click here when you're ready, and then it's a live data collection. Okay, go ahead and drop it back down. Sorry. Okay, so if you're not ready, as soon as you enter that information and you hit OK, you'll see the stream of data coming from all three sensors. Okay, if you're not ready, you just hit the pause button. It's like a videotape player. You hit the pause button up at the top, and that will halt everything, so that when you're ready to go, you would just hit the start button. Okay. So this is what the collection looks like. It's live collection, which is important because you know you're getting the data. Okay, you know you're getting the correct data. That's one of the sensors that's not left in the truck. I mean, that's happened to me before. Or when a sensor is on a different horse. Okay, so because we have multiple sets of sensors, sometimes both two horses going at one time. So it tells you that you're getting the right data, which is hugely important. The first channel is the head acceleration. The second is the right forelimb angular velocity. The third channel is pelvic acceleration. Each channel is synchronous, which is was a very difficult thing to do, but it's synchronous. So occasionally, what you'll see if the horse is getting out of range is about 100 meters, or if you have a lot of interference, you'll start to see one channel lagging behind. And so that's like a signal of, okay, the horse is getting too far away, start coming back with the horse.
So where's the collect data button? Was that on the previous slide? Did I miss that?
You hit, yeah. As soon as you click this OK button down in the left-hand corner,
It'll start accumulating data.
It'll start, yeah. And if you're not ready, you would then hit the pause button, which is up here. Pause. Yeah. If you just remember those general categories: enter horse owner, connect sensors, enter trial, collect, you can figure it out. It's pretty self-explanatory. Okay, so if the horse gets out of range, the thing is, you just get the horse to come closer, because you don't have to worry about the sensors becoming asynchronous, which, by the way, would completely screw up the fault detection analysis if the sensors were not synchronous. Okay? But there's buffers on the sensors and timestamp, a very accurate timestamp, so that even if it's collected asynchronously, the computer will put it all back together synchronously and do a correct analysis. We've tested that in depth also. Okay, so now once you got the data collected, you've stopped the data collection and you start the analysis. You start the analysis, again, the instructors will help you here by pushing another button. It says save and analyze now. Save it, analyze it, okay? And that launches into the analysis, okay? And there's two parts in the analysis, in the entire analysis, where it stops and it asks for your input. Okay, only two spots. Okay, the first spot, and I'm showing it here, is to show the veterinarian what the stride selection is, because this fault detection technique only works when the horse is trotting. Okay, if the horse is cantering or walking or standing still, it doesn't work. Okay, so it'd be very cumbersome, very difficult if the veterinarian had to go look at the data and say, okay, I want this when the horse was trotting, and I want that, and this is when the horse was cantering, I don't want that. And so we have developed these algorithms that will pick up, and you kind of have to understand this a little bit, that will pick up when the horse is trotting, and it displays it to the veterinarian. Okay? The way it does this is it uses the gyro sensor on the right front leg, which is has a very clear signal for when the leg is, if the leg is up in the air or on the ground. Okay, so it calculates. It's a very clear peak. Okay, so it looks at the peaks and it calculates the distance between the peaks, and it calculates the instantaneous stride rate, which, by the way, is proportional to the speed of the horse. But it calculates the instantaneous stride rate. What is the stride rate for that stride? Okay, and it does that throughout the entire trial that you've collected. Okay, if the horse's most common activity during that trial that you collected is the trot, then the algorithm to pick the trotting strides works very well. It looks for the median stride rate, which is it's the middle. Okay, it looks for the median stride rate over the entire trial, and it says only look at strides that are within a certain window of that median stride rate, which, by the way, is 10% of the median stride rate. Okay, so when the horse stops, or if it speeds up too much, or if it is turning around or cantering, the stride rate goes away from that median stride rate, and it won't pick it up. Okay, so 95 to 99% of the time, the algorithms work fine. They pick up when the horse is trotting. Occasionally, it doesn't, but it allows the veterinarian to adjust that. And it does this by showing the veterinarian first what is being selected. Okay, so here is an example of a horse that, this is the head acceleration. It shows this plot, this head acceleration plot, and then this window. Is the stride selection correct? And this is where the horse was standing still right here. Then they trotted the horse down in one direction, and as the horse was trotting, the head acceleration increased. Then they turned around with the horse and trotted back. Okay, and the software says, okay, I'm going to analyze between this blue and this red asterisk. I'm going to start here, and I'm going to end here, and then I'm going to look for the next blue star, and I'm going to start there, and I'm going to end there. Okay, it throws away in between the red and the blue star. So you knew what activity you just did. This was a horse that trotted back and forth twice, and it made that selection. Well, that's a good selection. It threw away when the horse was turning around. Okay, so you just hit yes. Is this stride selection correct? Yes. 99% of the time, it is correct. Okay. It's when a horse is lunging, and it starts cantering, you'll see where it'll throw that out, and you have to remember that and say, okay, the horse was cantering there, it threw that out, but that's good. Okay. However, here's an example of the computer doing a pretty good job, but it threw away the beginning here. Maybe the horse took too long to get into the trot, and then maybe the handler slowed down as the horse was ending the trial. So it didn't select the beginning or the end. Okay, maybe you want to analyze it. So you would say, no, this stride selection is not correct. Okay, and then you would have this. There's the slider bar here. Okay, which all you have to do is drag it to the right, and what that increases the window size, so more strides are selected. Or drag it to the left if too many strides. If you didn't say it was actually analyzing when the horse was turning around, you didn't want that. Well, then you drag it to the left to make the window tighter. Okay, so this is the first place in the analysis where it asks for user input. Is the stride selection correct? Okay, the second place where it stops is after the analysis of the front limb evaluation and the presentation to the veterinarian of the forelimb lameness plot, which is this plot where here we'll go over that a little bit. But the reason and it's asking, do you want to remove outliers? Okay, and even though there's, what are outliers? An outlier is a horse acting up and turning its head all over the place, and so that its head movement includes other factors that may not be associated with lameness. Even though the fault detection technique that we use minimizes that, occasionally in a very bad horse, there'll still be highly variable head movement, and you may want to remove some of those. So here's an example of a horse that has, and then I'll explain what the forelimb ray plot is, but it has a pretty significant right forelimb lameness, but then has these things over here, like the horse has also a left forelimb lameness. Well, that's probably not correct. So do you want to remove outliers? You simply say, yes, I do. I want to remove, I think these are outliers. I want to try to remove them. It doesn't make any sense. So you say yes, and then you see the slider bar back up again, and you drag it to the left, or if you want more strides, you drag it to the right, but you hardly ever want that. Drag it to the left until it eliminates the strides that are not like the other ones. Okay, so the slider bar works exactly the same way for stride selection as it does for removing outliers. You just drag it. Okay, so for instance, that's what I did here, and I got rid of the outliers. You don't have to, you remove outliers maybe, I don't know, maybe 5% of the time.
You can judge, it's not 1 or 2, it's 6.
Well, it's a statistical thing. It's really based strictly on, are these strides outside a certain number of standard deviations from the mean? So that's all it's doing. You're changing the standard deviation. If they're not outliers, you can't remove them. You won't be able to. It's impossible. So it's a pure statistical thing. You're just removing strides that are not with the group.
So if we don't remove the outliers, it won't affect the final diagnosis, or will it? Or I mean, are the numbers different on the bottom line if we with or without the outliers?
Well, yeah, you can change it, because here is like, see this, I'm going to go over this red ray here. That's the average length of the ray.
Mm.
Okay, so this is screwing up the average. Mm. So that ray got longer by removing these outliers. So yes, you can
ideally
definitely.
You want to remove your outliers.
For consistency sake, yes, it's better to remove outliers, but you don't have to do that. In, I would say, the majority of cases, you're going to get the same result. But if you don't remove the outliers, the standard deviation, which we do look at, will be larger,
Because that could screw up if you're doing a block, like on a subtle thing, if you don't remove your outliers.
Right, yes, definitely if you're doing a block, it's more important, yes. Yeah. It takes a little bit of finagling, but it is the best. It's the most objective and the most accurate when you do remove the outliers, yes. But it's a purely statistical thing. If it's not an outlier, you can't remove it.
And you said you only do this about 5% of the time.
About 5% of the time. And say, for instance, let's say you're interested in the hindlimb lameness. Okay, you don't need to do that. Okay, because that's just for the head. Okay. So I went through a lot of this very quickly. Okay. Okay, I want to go back one thing and say this because this actually happened a few days ago with one of our users. You know, occasionally you'll get, this happens with, for instance, flexion tests, even though we're not going to do flexion tests here, but you know, when a veterinarian is evaluating a flexion test, he looks at the horse trot off in one direction, and usually like the first couple of strides are important, and usually you get maybe 6 to 10 strides. Okay. You know, and sometimes the horse doesn't take off very well. You have to get after it. So this median stride selection and window around it, it works best when you get a lot of strides, because then you can accurately calculate the median and the window very easily. But when you get only a few strides, that's more difficult to do. So sometimes after a very short collection, you won't, it won't see any stars on the plot, so it didn't pick anything. Okay. And it's saying, is this stride selection correct? And obviously the answer is no, because it didn't pick anything. Okay, so you hit no, and then you try to move that bar as far to the right as you can to pick up strides. Okay. Occasionally, with flexion tests, you may not be able to do that, even with making the value as high as possible, and you won't be able to. And then you can't do any analysis. Okay, you just won't. You got to do it again. Okay, that happens infrequently. I'd say maybe 1 out of 25 flexion tests. Just guessing. So you just have to understand, and if you didn't understand how it calculated the median stride rate, you would say, "What the heck is going on here?" You know. But now you know. It can't pick a median stride. Right? Okay. So
is the speed as a multi-track relevant? Like, you want to be on a certain speed, or when you go faster, you go slower? Do you see a variation there?
well, in my opinion, it is relevant to keep it about the same, because we don't measure the speed of the horse, but we do measure the stride rate, and it's reported on the report. And it is possible that if you have a horse, for instance, before and after a block, where if you switch people trotting a horse, you get somebody who likes to go really fast and somebody who likes to go slow, that can cause a difference. Yes. So you try to do about the same speed. People have looked at what speed is best to pick up lameness, and there is no best speed, because some horses, the lameness is more visual and measurable at slow, and some lameness is more visual and measurable at fast. You can't tell.
But it's agreed that the slower they trot, the better you're able to see the lameness.
No, sometimes the faster it makes the vision more measurable.
Compare horses, for example, trot off moving, and as they slide towards the end, you see the lameness get it, so the last victory. How would this...
Say that again.
Say the lameness sometimes the horse will trot off quite well,
Yeah.
and as it slows up, just before it stops, the lameness becomes more obvious the last few strides.
Well, for instance, for you will see, especially for hindlimb, you will see that on the plot that the lines are, for those strides, are actually longer. You will see that.
You see that, then you can sleep just those, maybe the second half of the cross.
Well, no, that's good. That's more difficult. Yeah, you can't really do that. But that's a good point to think about something in the future to do.
Because theoretically, when you jog a horse off, just like you're saying, you don't just start at 3 meters per second. You don't go from 0 meters per second to 3 meters per second. You accelerate, then you decelerate. So theoretically, there should be a zone of data at the beginning, at the end, that's not 3 meters per second.
Right, and that does happen when, like this example I showed here. Okay, this was two different horses, where this horse started out really briskly, and it selected everything.
So that horse went from 0 to trot speed, whatever his trot speed was, instantaneously.
Within 10% of its median stride rate
That's
in
what
the
I'm saying.
first
In the
in the
first
first
stride.
1 or 2 strides.
Wow,
Yeah.
that's,
And this horse didn't. It took a while to get,
okay.
but it's within 10% of the median stride rate. To me, it is amazing how many horses are like this and not like this. They get going, and their business, and they get going and reach their median stride rate, or within 10% of it pretty quickly. Okay, so so the only 2 parts in the software where it stops and asks you for your input, and most of the time you don't have to mess with any of that. If you don't have to mess with any of that, the analysis might take like 5 or 6 seconds before the report is seen. Okay. Okay, so let me see what this. Okay, once you log this real quick. Okay, once you have removed outliers or decided not to remove outliers, and you say go on, it goes through and does the hind limb evaluation without stopping. And there is no place in the software where you stop to remove outliers for hind limb evaluation. And the reason we do that is because it's not needed, because the outliers are so infrequent. So then it goes through, does the analysis, shows a report, you look at the report, and save the report. Here's a typical report, okay? What's on the report? Well, let me first back up and say there's a lot of things that happen before the generation of this report. The sensors are accelerometers. This fault detection technique is based upon position. Okay, so inertial sensors don't measure position; they measure acceleration. Okay, so we first have to, here's what happened. The raw data was downloaded. It was integrated, actually twice, with this iterative error correcting algorithm that was, went over and over and over again to give the optimum data. Then the non-periodic components of the movement were thrown away, and it was looked at again. Okay, and then it broke the whole thing down into separate strides and measured individual values of the maximum and minimum height differences. And then it presented it in this form. So there are a lot of things that happened in between there. Calculates the mean and standard deviations of all the values. Okay. So this is what it kind of shows you. It gives you this. It gives you a qualitative description of the lameness in these plots. It gives you a quantitative description by giving you numbers. And then it gives, this is our so-called expert system, expert because expert in data analysis, not in lameness evaluation, but it kind of interprets all the numbers and gives a suggestion about strength of the evidence and the amplitude of the lameness. Which, by the way, you can shut this off if you don't like it. Some people really like it, some people don't like it. That's okay. Okay. Let me just go a little bit over the plots. Okay. This is the forelimb plot. This is the hind limb plot. They're different because the biomechanics are different. Okay. In the forelimb plot, each one of these blue lines is a stride. Okay, and the number of strides is up here. Stride rate's right here, but the number of strides is right here. But each blue line is a stride. The length of the line is proportional to the asymmetry of head movement for that stride. So long lines are lame, short lines are not lame. There's a relationship there. The longer the line, the more amplitude of the lameness. Okay, and which way the line is pointing in this circle is an indication of what's affected, the acceleration or deceleration when it was occurring. So, and I'm not going to go through how that's calculated, but it's part of the fault detection technique. But if they're pointing up in this quadrant, that's a right forelimb impact lameness. And that's because it's primarily affecting the deceleration of the head when the right leg is coming down on the ground. Okay, if it's pointing up in this direction, it's a right forelimb push-off lameness, and that's primarily because it's affecting the acceleration of the head when the horse is pushing off the right leg. And then left forelimb impact, right forelimb push-off. And then there's this little circle in there, in the middle, that's sort of like the threshold of between normal and abnormal, which was determined experimentally, or estimated experimentally by looking at normal and abnormal horses. Okay, the hind limb evaluation is a little bit different. There's two subplots. This is what's happening in the left hind leg. This is what's happening in the right hind leg. Okay? And if a horse is pushing off less hard on a hind leg, it will draw a red line up on that side. Okay? So the first stride would be here, the last stride would be here. So this horse here, on every stride that was collected, the horse pushed off less hard on the left hind leg. If the horse is coming down less hard on a leg, it will draw a green line down on that side. So this horse, every stride, it came down less hard on the left hind leg and pushed off less hard on the left hind leg. That's where we get impact and push off for hind limb. And then these lines right here are sort of a normal threshold. So that's the qualitative analysis. The quantitative analysis, there's two values. There's the A1, A2 ratio for left front and right front. The A1, A2 ratio is sort of a screening measure. It's like an overall measure of how asymmetric the signal is. And then we do something to try to push that asymmetry measure on one side or the other. Okay. It's really a screening measure. And then the other measures are the max diff and the min diff of the head and the max diff and the min diff of the pelvis. Okay. And also on the report are thresholds, with experimental thresholds that we have determined are sort of like the borderline between normal and abnormal. And for the head, it's plus or minus 6 millimeters, and it's on the report. And for the pelvis, it's plus or minus 3 millimeters, and that's on the report. So you look to see, are they above that threshold? And then here's the expert system, which if you don't want to worry about any of this and thinking, well, the other thing that's reported is the standard deviation of that measure. So if it's consistent, then the standard deviation is going to be small relative to the mean, and that's important because that's very strong evidence. Okay, if it's inconsistent, then the standard deviation is going to be, relatively higher than the mean, and that's going to be inconsistent. Okay, and one way to look at consistency on these plots is if the rays are all pointing in one direction, that's very consistent. It's going to have small standard deviation. If they're all over the place, then it's less consistent.
Explain max diff. Could you explain max diff?
Yeah, okay. The max diff is the difference in the maximum heights between right and left. Because when a horse is moving, the head and the pelvis go like this. Okay, so there is a maximum and then a minimum. Okay, and there's a lot of them. Okay, in a horse that's lame, or a horse that sounds, for instance, this is how the pelvis moves: down, up, down, up, down, up. And when it's lame, it becomes asymmetric. If it's an impact lameness, it's down on the good leg, down on the bad leg, down on the good leg, down on the bad leg. So there's differences in the minimum heights. Okay, if a horse got a push-off lameness in the hind, this is the way it goes. It can push up on the good leg, off on the bad leg, off the good leg, off the bad leg, push off the good leg, push off the bad leg. Okay. So there's a difference in the maximum heights. So we measure what that difference is between the right and left for every stride. Okay, that's what those measures are. The head is a little bit more complicated, but the measure is the same. The difference in the maximum heights in one stride and the difference in the minimum heights in one stride.
What about min-diff?
Min-diff, the difference in the minimum heights in one stride. Yes.
Okay.
So it's the difference, a horse with a right forelimb impact lameness. Okay, the head knot, okay. The head goes down on the good leg, then down on the bad leg. There's a difference in the minimum heights.
Okay.
And it measures that.
Okay. So it's the relative. It's okay. It's
from the
it's
ground.
An absolute. Yeah, it's an absolute number.
From the ground.
Yeah.
Yeah.
In whatever.
In
yeah,
millimeters.
it's actual height. Minimum
Yes.
height, maximum height.
Yeah.
Okay.
Yeah.
Now, what if the ground's not? I mean, a stupid question, but I mean, you're measuring heights, and you got accelerometers. So if the world surface is not perfectly
Yeah. Well,
like this
let's-
floor, then how does that affect the data? And
Well-
also, when you have a standard deviation that's higher than the mean, there's such a thing called a coefficient of variance when you collect data. And
Yeah.
so, could you speak to that?
Okay. Well, first the non-flat surfaces. Okay. You will find that your variation is less when you're trotting a horse over a flat surface. Your variation is less. Your
Which-
deviation is less. It's greater on a surface that is. But the only, the only reason it would really make a big difference, or that you would get a wrong result, is if it was a very consistent difference. So, for instance, let's say the horse would have to step in a hole on every right leg hit. So, the surface would have to be like this. And it would step it in a hole every time the
But
right
that
hit the
does
ground.
affect the data to a certain degree.
Yeah.
I mean,
Yeah.
it would have to.
Yeah.
I mean, but it doesn't just make you want to throw out the data. The data's still
Right.
valid. It just affects it.
Right. Yes.
So what about when I just look at this, the standard deviation of some of the data is just so high. I mean,
And
in some
that's-
time, not all the time, but
Yeah, and that's because it's not the equipment, it's the horse. The horse is doing that. The
so
horse
every
is
stride he does in the min diff and max diff is not the same. So every single stride he takes, if it's just a lame horse A, every one of his strides is different. Or if we looked at 18 strides, or whatever you've got up there, every one of those 18 strides is different.
then it's never going to be the same. Never.
Okay.
And when the standard deviation is greater than the mean, that means you've crossed zero. So let's say the min diff of the pelvis is 4 millimeters, which is 1 millimeter above the threshold. Okay. The mean is 4 millimeters, but the standard deviation is 6. That means that the mean could be anywhere from -2 to +10. 4, 6, yeah. So yes, it crosses zero. That doesn't mean that that's what the horse did. That doesn't mean that the horse is got to be normal. I mean, but your confidence for saying that horse has a consistent lameness has got to go down when your standard deviation is greater than the mean. That makes the data less confident, for sure. There's no question about that.
When the standard deviation is greater than the mean.
When the standard deviation is greater than the mean, it's not very much a problem usually for pelvic. It can be a problem for head. So, but in the expert system, that's at the bottom of but we take that into consideration, and that's what we're going to discuss next. This expert system for baseline straight trot, it evaluates 2 factors for each leg. One is the strength of the evidence. And there's, what are the different levels? There's no evidence, okay, so none of the values were indicative of lameness. There's weak evidence, there's moderate evidence. So for instance, if you had a standard deviation that was greater than the mean, but the mean was quite high, then that would be moderate evidence. Okay? And then there's strong evidence. Strong evidence is all the factors that measure lameness, A1, A2 ratio, the max diff, the mean, the min diff, they're all fall in line, and that's strong evidence. Okay? So that's taken into consideration in the expert system. Okay? What the relationship of the standard deviation is to the mean. And then the other measure in the expert system is the amplitude of lameness. So each leg gets a measure for the strength of the evidence and the amplitude of lameness. And the different levels for amplitude are no lameness, mild lameness, mild/moderate, moderate lameness, and moderate slash severe. There's no severe because that you don't need that.
So the horse is basically acting as its own control as a symmetric movement.
Yes,
So
for
what
sure.
you're measuring is the asymmetries.
Mm-hmm.
And is normal gauge symmetric or asymmetric?
Normal is symmetric.
For sure.
Yes, for sure.
Okay. Well, because the debate is also there's some hypothesis that normal
Yeah.
gauge is not symmetric all the time, right? There's some asymmetries.
Right.
So
Yes.
do we
Yes.
know what is the strength of the assertion that
That's what the
the
thresh.
gauge is symmetric?
Yeah, that's what those thresholds